Have you ever wondered what really makes one piece of code good and another not so good? It's not just about getting the right answer. It's about how efficiently it gets there. In this explainer, we're going to crack that code and learn how to judge software like a true pro.
All right, let's just jump right in with a simple question. Imagine you've got two apps. They do the exact same thing. So how do you decide which one is actually better? I mean, really fundamentally better. That's the core puzzle we're going to solve today.
Now, you might be thinking, easy, I'll just time it with a stopwatch. But nope, that's super unreliable. Your laptop might be way faster than mine, or maybe you've got a bunch of stuff running in the background. Okay, so what about counting the lines of code? Well, that's just as misleading. You could have one tiny little loop that runs 1,000,000 times, making it way slower than, say, 20 simple lines that only run once. We need a better way, a universal standard.
So here's our game plan. First, we'll talk about organizing your data. Then we'll get into the recipe, the algorithm for using that data. After that, the main event, learning how to actually measure performance. This will lead us to a pretty cool new skill, analyzing code in just a few seconds. And finally, we'll wrap up with why this all really matters. Let's do it.
Okay, first things first. Before you can cook, you need ingredients, right? It all starts with our raw material, the data itself, and how we decide to store it. So what even is data? Well, you can just think of it as raw information. It's the most basic building block of any program you'll ever write. A really good way to think about it is like water. You got this essential resource, water, but now you need a way to hold it. And here is the big idea. If data is like water, then a data structure is simply the container you put it in. Think about it. The container you pick depends completely on what you want to do. If you're thirsty, you grab a glass. If you need to wash your car, you get a bucket. And if you're going on a hike, a bottle is your best bet. Choosing the right data structure is the exact same principle. You pick the container that makes the job you need to do as easy as possible. Okay, so you've picked the perfect container and your data is all nice and organized. Now what? Well, you need a set of instructions to actually do something useful with it. And that's where an algorithm comes in. Don't let the word scare you. An algorithm is just a recipe. It's a step-by-step set of instructions for getting something done, just like making tea. Two people can have different recipes for tea. Maybe one person heats the water first, another adds the milk at a different time, but in the end, they both get a cup of tea. It's the same in programming. Different algorithms can solve the exact same problem.
So this brings us to the most important question of all. If you have two different recipes, two algorithms, and they both work, how can you definitively say which one is better? This is where we learn to measure performance like a pro.
To really get the mindset for this, let's use a super simple analogy. Let's say you go shopping and you buy two things, a $30,000 car and a $300 bicycle. A second later, your friend calls you up and says, "Hey, what did you just buy?" You only have time to give a one-word answer. What do you say? You'd say, the car, right? Of course you would. Why? Because compared to a $30,000 car, the $300 bike is basically irrelevant. It's a rounding error. When we analyze code, we do the exact same thing. We look for the most expensive, the most dominating part of the process, and we pretty much ignore all the little stuff. Now, this whole idea has a formal name. It's called time complexity. It's the standard way we describe how an algorithm's runtime grows as the amount of data we feed it gets bigger and bigger. And a special language we use to talk about this is called Big O notation. And here's a handy little cheat sheet of the most common Big O types. At the top, you've got the superstar, O of 1, or constant time. It's flat. Doesn't matter how much data you have, it takes the same amount of time. Amazing. Then there's O of log n, which is also fantastic. It grows, but super slowly. O of n, or linear, is your solid, everyday performer. It grows at the same rate as your input. But then you get to O of n squared, quadratic. This is where performance can really start to hurt, because it grows way faster. Okay, enough theory, let's get to the practical payoff. Right now, we're going to learn how to spot these patterns just by glancing at a piece of code. This is your new superpower, the 30-second analysis. First up, the easiest one. You see a chunk of code, just a few lines, no loops at all. That means its speed has nothing to do with how much data you throw at it. That's constant time, O of 1, blazingly fast. All right, next. This is the one you'll see everywhere, a single for loop that runs through a list of n things. Well, if you have 10 items, it takes 10 steps. 1,000 items, 1,000 steps. The work grows in a straight line with the input. That's a dead giveaway for linear time, O of n.
Now, what happens when you put a loop inside another loop? Uh-oh. For every single item in that outer loop, you have to run through the entire inner loop all over again. The work doesn't add, it multiplies. This is quadratic time, O of n squared. And this is how programs can get slow really fast. And finally, one of the most efficient patterns you'll ever see. It's any loop that cuts the problem in half with each step. Think of finding a name in a phone book. You don't start at A. You flip to the middle, throw half away, and repeat. The number of steps barely goes up even if the phone book gets way bigger. That's logarithmic time, O of log n. It's incredibly fast.
And this chart just puts it all into perspective. I mean, look at that difference. The logarithmic bar, O of log n, is barely moving. The linear one, ON, is growing steadily. But look at the quadratic one, O of n squared. It's shooting for the moon. Seeing it like this makes it crystal clear which recipes you want to be using.
So, we've gone from data containers to recipes to big O notation. The big question is, why does any of this actually matter? How does this theory affect you in the real world? Well, understanding this stuff is a genuine programming superpower. For real. You'll start writing software that's faster and more efficient. You'll become a much better problem solver because you'll be thinking about these trade-offs from the very beginning. And let's be honest, this is a make or break skill they test for in pretty much every single technical job interview out there. So I'll just leave you with this question to think about. Now that you have the basic tools to tell a fast algorithm from a slow one in just a few seconds, what's the first piece of inefficient code you're going to spot out there in the